It is well known that when light is added to light, it boosts the illumination. It is a common knowledge. For example, you have an object, you have a source of light, shine the object to illuminate it. If the illumination is not enough, you may use another source of light and shine it with more light, add more light to it. It then boosts the illumination. But the fact that light added to light can also result in darkness was not known, was not understood, appreciated until a British physicist, Thomas Young, performed his celebrated double slit experiment in 1801. This made a very profound impact on the contemporary science and allowed flow of knowledge unhindered for many years. Before we move forward and gain an insight into this experiment, let us see what kind of impact it made. It may be of interest to note here that in May 2002, Stony Brook University and Brookhaven National Laboratory in the United States of America conducted a joint study asking physicists across many countries to nominate the physics experiments that have made the most profound impact of all time toward perceiving the design of nature, towards understanding nature. Once feedback was received from many physicists, the list was published in the September issue of Physics World of the same year, which captured basically a bird's eye view of the most imaginative physics experiments spanning approximately the last 2000 years. It is quite remarkable that Thomas Young's double slit experiment with light that conclusively re-established the wave nature of light was ranked 5th in that list. The wave theory of light was originally proposed by Dutch physicist Huygens in 1619. However, the corpuscular theory, that is the particle nature of light, that advocated particle nature of light, that was proposed by Newton in 1704, completely overshadowed this wave theory of light. Newton's authority in the scientific world was so pronounced that nobody could challenge, even after his death, the corpuscular theory. And understandably, Huygens' wave theory took a backseat. Wave theory of light took a backseat. And this notion continued for almost 3/4 century after his death, until Young did his famous double slit experiment in 1801. In this context, I should mention, it is also quite remarkable that exactly another century later, the particle nature of light made a complete turnaround when in 1905, which is more popular as a year of scientific miracle, courtesy Albert Einstein. Einstein was able to resolve the puzzle of the photoelectric effect by considering light to be composed of a stream of photons. You all have studied photoelectric effect in your high school physics, and so you know that wave theory of light could not explain photoelectric effect. And Einstein's explanation of this basically cemented the quantum concept of light. And it was established that light was capable of behaving both as a particle as well as wave. Taking a clue from this, Louis de Broglie, French physicist, proposed in 1924 that quite like light, matter can also behave both as wave and particle. This work planted a seed of quantum mechanics, perhaps some of you know, to describe the physical properties of atomic and subatomic particle that constitutes the microscopic world that we know today. It is also quite remarkable that another interference experiment, but now with an electron and not with light, as was the case with, arguably become the all-time #1 physics experiment. And it may be of interest to note here that the outcome of this experiment, establishing unequivocally the wave-like nature of electron, put quantum mechanics on a firm footing. This, of course, altogether another story. Let us quickly catch up now with Young's double slit experiments and try to understand its consequence. You see, the experimental arrangement used by Young for his experiment was fairly simple. This is a qualitative illustration. The qualitative illustration has been shown here in a very schematic manner. An opaque barrier, this is the opaque barrier, with two parallel slits pierced into it on this barrier, is placed between the source and a viewing screen. This is the viewing screen. This is our opaque barrier, this is the source. The slits are symmetrically placed with respect to the source. That means the distance between the source and the slits will same. Now the source is not a laser source, of course. This source will emit light all around it. We now know this. But for clarity, only the array of rays in a two dimension that shines on the barrier have been shown here. Now, if light were to follow Newton's corpuscular theory, like it would have behaved like a particle, then it would, of course, leak through the slits and the slits alone and cast two bright stripes on the screen in the location as shown here. In reality, however, light reached to the plate in places forbidden by the presence of this opaque barrier. and produced alternate bright and dark fringes, bright, dark, bright, dark, bright, dark. But what is most important is that the brightest region occurred at a place of the viewing screen that was just opposite to the opaque region between the two slits where light could never reach directly. Obviously, the explanation of this was not possible by using the corpuscular theory of light. This observation can be explained by considering that light travels as waves. This wave theory-based interpretation of the formation of alternate bright and dark fringes on the viewing screen can be understood by taking this wave picture explanation of this experiment. However, before we do that, let us digress a little to refresh our mind on the property of a wave. A wave, as we know, can often be described as a sinusoidal propagation of some disturbance. The transverse wave, in case of a transverse wave, the disturbance is actually normal to the direction of propagation. If the wave is propagating in this direction, the disturbance will be normal. So this transverse wave is more abundant in nature. One exception is, of course, acoustic wave, probably you know, which is a longitudinal, where the disturbance lies in the same direction as the direction of propagation of the wave. Now, the manifestation of the oscillation of the disturbance is shown here for a typical transverse wave, as you can see. The points of maximum and minimum disturbance, this is maximum disturbance and this is minimum disturbance, are known as crest and trough. So this is a trough and this is a crest. And the maximum value of the disturbance is called amplitude of the wave. And the distance through which wave advances in one cycle, one full cycle of oscillation is called its wavelength. So the wavelength then basically is the distance between two corresponding points of the wave which are in same phase. For instance, this point and this point, they are in same phase. So this is what wavelength. And same also will be true between this point and this point. They are also in same phase. So that is wavelength. Number of oscillations the wave completes in a second is called its frequency. That means in every second, how many oscillations are taking place. So if in each oscillation the wave advances by a distance of lambda, then now f oscillation, the wave will advance by a distance of a into lambda, which obviously is the velocity of the wave. The distance the wave advances in a second is the velocity of the wave. Well, let us now catch up with the wave theory based interpretation of Young's double slit experiment. Result observation of Young's double slit. See, the two slits are equidistant from the source. Because they are equidistant from the source, therefore rays of light belonging to the same wavefront will strike them. Well, wavefront is the locus of all the points where waves starting simultaneously from the source arrived at that instant of time. For example, let us assume that we have a point source. We have a point source. From there, from this point source, the light is traveling in all directions. We just take few of them. Suppose we want to see where the wave has arrived, say after a time t. After a time t, if velocity is c, then it has arrived distance ct. Similarly, it will arrive here, here, all are ct. So the wavefront is the locus, all this. Therefore, quite naturally, wavefront of a point source will be a sphere. And the rays of light will of course be normal to the surface of the sphere. So now you understand when we say that as the two slits are equidistant from the source, rays of light belonging to the same wavefront will strike them. Because it is equidistant. So the same wavefront will meet these two slits. And according to Huygens theory, the two slits will now act as secondary sources as against this original source and give out their own wavelength in unison. They will produce it simultaneously because the same wavefront has interacted with the slits, with the slits. Now you see the brightest strip, brightest stripe formed at the middle of the screen. So if this were the screen, the brightest fringe formed here, which is equidistant from the slits. Therefore, the wavelengths originating from the two slits will always arrive here at face. This is understood. Crest overlap crest and trough with trough. So they will reinforce each other. This is called constructive interference. And dark bands, suppose here there will be dark band, here there will be dark band. So what happens in the dark band? Dark band will be created on the locations where crest of one wavelength. Now, just a moment. Now you see the trough and crest of the wavefront is shown by dark and the broken lines. And the wavelets produced by these two slits, the wavelet produced by the slit above this, the top slit is shown as in blue color, and the wavelets emitted by the bottom slit is shown in red color. And once again, the crest and troughs are respectively indicated by solid and broken lines. Now you can see that for the bright fringe, this line, always a crest of one slit meets the crest of other slit. So they are always in phase. Here, trough of one slit meets the trough of the other slit, and so on. So that is why the bright fringe is formed here. The waves always arrive at phase on this line, this central line. Now, in case of dark fringe, what happens? Crest of the wavelet arriving from one slit is lined up with the trough from the other slit and vice versa. You can see in this line where dark fringe will form. Crest of this gets lined up with trough of this. And in this case, trough of this and crest of this, and so on. That is why here you will have an annihilation of the two waves. That is called, they will neutralize each other. This is called destructive interference. The annihilation and reinforcement of two light waves upon meeting each other is called interference of light. As you can see here, the two waves, when they are meeting each other, exactly out of phase, they will annihilate. And when they are in phase, there will be reinforcement. So now you know how light added to light can also result in darkness. So it is well known that light added to light boosts the illumination, but the light added to light can also result in darkness when they annihilate each other. As a result, a destructive interference. Now, let us translate this knowledge into an analytical expression, connecting formation of fringes with the path difference of the two rays that form them, with the length of the path difference of the two rays that form them. For this, we take a closer look at the Young's double slit experiment. This is an oversimplified 2D representation of the setup of double slit experiment. This is the incoming wavefront, which two slits, and the two slits then emit, as we have seen, their own wavelengths in unison. For a easier understanding, instead of wavelets, we have shown here just two rays emanating from both the slits. Just for clarity, the same wavefront interacts with the. Now, let us now focus on the point B, where the bright fringe is formed. Now, this point B is equidistant from both the slits. Therefore, the length of the path that the two rays have traveled, one originating from the upper slit and the other originating from the lower slit, they have traveled equal path because this is equidistant. So they arrive here in phase. So otherwise we can say that when the path different, so they arrive in phase and they interfere constructively, and so you have a bright fringe here. So we can say that when the path difference is 0, you have a bright fringe. Now let us consider the next bright fringe below the central B, which has occurred at this point, B1 on the screen. This is my screen. For this point, you see the ray which originates from the upper slit travels a longer distance. This distance is longer than this. This is longer. And this is shorter. But they again interfere here and produces a bright fringe. This would be possible if and only if the path difference of these two rays is once again is now lambda. Earlier it was 0, now it is lambda, one wavelength. Why? Because you see, if the path difference, say for one wave, for say this one, this ray, it is just very qualitative depiction. 1, 2, 1, 2, 3, 4. So this is, I am denoting this ray. And this one, the path difference is more. So I show it, say by green. And this one has traveled a distance which is longer than this. How much longer? It would have traveled just one wavelength. Then they will be in phase. And so you have a bright fringe here. So here the path difference is lambda, these two rays. While in the previous case, path difference was 0. Then if you go to the next, not shown here, next bright fringe, it can be shown that the path difference of the two rays, now the path difference will be more of these two. And this will be more and this will be now 2 lambda. So we can say, and the same thing will happen if we focus on the fringes above the center, upward. Everything would be same except that now this ray will travel shorter distance compared to this. This would now travel longer distance. But nevertheless, the difference of path length will be again lambda. And for the next one, next bright fringe, it will be difference of the path will be 2 lambda. Therefore, we can say that when the path difference is 0, lambda, 2 lambda, 3 lambda, you have bright fringe. Now let us focus on the dark fringe. Say, let us focus on this one. So here, the ray that travels from here is this, and the ray that travels from here is this. So this ray has traveled longer distance than this. And because they have formed a dark fringe, it can be easily shown that this ray has traveled a distance which is more than this by half of the wavelength, lambda by 2. I think you are able to perceive it. If the difference will be lambda by 2, that means there is a shift of the wavelength by lambda by 2. So with this shift, the trough of 1 matches with the crest of 1. If it were 1 lambda shift, then crest and crest will match, trough and trough will match. But if it is half lambda, then crest of 1 will match with trough of 1 and crest of other will match with trough of that. So they will annihilate. So in this case, the path difference will be lambda by 2. And for the next next dark fringe, which will be here, it will be lambda plus lambda by 2. That means 3 lambda. Next one will be 5 lambda by 2. Similarly here, the path difference again, now this ray will travel longer distance than this ray. But the path difference will once again be lambda by 2 if it has to be a dark fringe. So we can say that for path difference of lambda by 2, 3 lambda by 2, 5 lambda by 2, it will be dark fringe. This finding can be generalized into an analytical expression which says that if the path, so that means what? If the path difference is integer multiple of lambda by 2, that is 2 into lambda by 2, 4 into lambda by 2, 6 into lambda by 2, and here it is odd multiple, 1 into lambda by 2, 3 into lambda by 2, 5 into lambda by 2. So we can write that if the path difference is even multiple of lambda by 2, that's 2 and lambda by 2, you have right fringes. And if the path difference is odd multiple of 2, then you have dark fringes. This is very important. Now, obvious question is what happens when the path difference lies in between? So when the path difference lies between lambda by 2 and lambda. Lambda by 2 is the dark fringe, and here it is the bright fringe. But what happens when the path difference lies in between? So as you can see from here, this is a plot of intensity of the fringes as a function of the path. So for path difference lying in between, the fringe intensity will vary from 0 to maximum, or maximum to 0, as the path difference changes from lambda by 2 to lambda, or lambda to 3 lambda by 2, 3 lambda by 2, 2 lambda. This suggests that manipulating the path difference between the two interfering waves, the intensity of light upon their superposition can be varied in a controlled manner. If you can control the path difference, then you can control the intensity of the light that the two beams will generate after superposition. So next class we'll begin from here. Let's end today.